Next we have the energy stored in an inductor coil. So that would be energy stored in the magnetic field of the inductor coil. And what I like about this one is we start off with this nice bit of rhyming here. The energy is the integral from 0 to I of L of I di. There's got to be a high joke in there somewhere. Anyway, the point is, when we do the integration of all of this, what we get is that the energy is equal to a half Li squared. You want to remember that. And what I like about it is that that's the energy stored in an inductor coil, and it's exactly the same format as the kinetic energy formula, a half mv squared, which certainly is a very pleasing symmetry, because this is to do with moving charges and this is to do with moving masses. So in a certain sense we can argue that the energy stored in a capacitor is analogous to gravitational potential energy, GPE for short, because I'm not writing it all out. And we can argue that the energy stored in an inductor is analogous to kinetic energy. Okay. Why is this a very good analogy? Well, if you think about how a capacitor works, it works by fixing the position of a charge, and then an electric field builds up and so on. So how does gravitational potential energy work? It works by fixing the position of a mass. Energy stored in an inductor is clearly dependent upon the current. Current is moving charge, kinetic energy is moving mass. Now, just as we have a capacitive reactance, we also have an inductive reactance. So X subscript L for inductive reactance, VRMS over IRMS, in other words, Ohm's law, root mean square voltage over root mean square current. Conveniently, that is exactly equal to the peak voltage over the peak current, and we'll show you why that is in a moment. And when you do the math, you end up with a formula that says the inductive reactance is equal to 2 pi FL. In other words, 2 pi times the frequency of the AC current times the inductance of the inductor. So let's say we have an AC current that can be described as follows. I of t equals I naught sine omega t. Well, according to Faraday et al., we know that the EMF is equal to L di by dt. And don't forget the minus sign. So that then is minus L d I naught sine omega t by dt, which we should be able to do fairly easily from our knowledge of maths, and get that that is omega L minus omega L, and that will become plus IP cos omega t, and a bit more maths will tell us that that is omega L IP sine omega t plus pi by 2. So how does this help us? It helps us due to the fact that the EMF is V of t, in other words, the potential difference depending upon the time variable. And from that we can go that the peak value of the voltage is going to be omega L I P, and when this trig term equals 1, whether it's cos omega t or sine omega t plus pi over 2, we'll get our peak voltage. And then that relates up here quite nicely, because that means that Vp over Ip equals omega L. And since we know all the way back since the start of Unit 1 that omega is 2 pi f, there's our 2 pi FL, which is our inductive reactance. And if you're wondering why we bothered to change the cos omega t to the sine omega t plus pi over 2, it's because this plus pi over 2 tells us that the current in an AC circuit lags the voltage. In other words, the peak of the current comes pi by 2 after the peak of the voltage. And now that we've confirmed that the inductive reactance equals 2 pi FL, we can say that the inductive reactance varies as the frequency, which we can graph if we really want to as XLF, and we should get a straight line like so through the origin. And that tells us that a very significant application of inductors is as what are called low pass filters. In other words, they allow low frequency currents to pass easily, but make it very, very difficult for high frequency currents to pass. And if you've ever wondered how it is that we can tune a radio to a particular radio station, or tune any receiver for that matter to a particular signal frequency, it's by use of tuning circuits. And tuning circuits depend on a concept called the resonant frequency. The resonant frequency occurs when, you're going to love this bit, the resonant frequency occurs when, yes, you guessed it, XC equals XL. In other words, when the capacitive reactance is equal to the inductive reactance. So how on earth do we make that happen? We make it happen by having variable capacitors and variable inductors. And if we then adjust the values of the variable capacitors and the variable inductors, we can tune our circuit to have a resonant frequency of whatever value we happen to want, based upon the capacitance and the inductance of the capacitor and the inductor in the circuit. So how does that work? Well, XC equals XL. So 1 over 2 pi FC equals 2 pi FL. See? So that means that 1 equals 4 pi squared F squared LC. And that means that F squared equals 1 over 4 pi squared LC. That means that F equals 1 over 2 pi square root LC. And that frequency is the resonant frequency. So depending on the values of inductance and capacitance that we pick for the circuit or adjust the circuit to have, we will then get a resonant frequency, and that is the frequency that the circuit is tuned to and built into a receiver. In other words, connected to an aerial. That is the frequency that this receiver will pick up. Once we've picked up a signal, of course, we need to display it in some way or represent it in some way. And if we're talking about a radio wave that we're going to turn back into a sound wave, then we can use woofers, which are a very silly way of saying low-pass filters. In other words, inductors and tweeters. which is a very silly way of saying high-pass filters. In other words, capacitors. And what happens is we've got our electrical signal from the aerial. We've selected a specific frequency, a carrier wave, using the inductance and capacitance in the receiving unit. We then pass that electrical signal on towards the speakers, but we split it into two parallel sections. One section will be passed through an inductor, which will allow the low frequencies to pass, and that will go to a large diameter speaker cone and give us a good reproduction of the low notes. The other section, the other parallel branch, will be passed through a capacitor, which will allow the high frequencies to pass but block out the low frequencies. That will go to a small diameter cone and will give us a good reproduction of the high frequency sounds. And last item in this video is the torque in an electric motor. So from unit 1 we should know that the torque is equal to the applied force times the radial distance from the axis. And from unit 2 we should know that the force on a current carrying conductor of length L in a magnetic induction B at an angle theta, remember if it's at right angles that sine theta will just become 1, from unit 2, F equals Bill sine theta. So we put these two equations together, we get T equals BILR sine theta for a single turn of wire, in other words a single loop of wire. And if we have a coil of wire with N turns, in other words a solenoid, or a coil of wire, say between magnets, as in an electric motor, then we pop in an N for the number of turns. So T for torque equals nibia sine theta, NBIA sine theta. And that is where people usually stop. And it's not a bad place to stop. But there's a very little bit of algebra. We know, for example, that B, the magnetic induction, times A, the cross-sectional area of the coil, is the magnetic flux. And we know that N phi over I is the inductance of the coil. In other words, N phi is Li. So again, a little bit of algebra, Li squared sine theta. So torque is equal to the inductance of the coil multiplied by the square of the current passing through the coil, and sine theta if it's at an angle to the magnetic field rather than perpendicular to the magnetic field.